session which is on machine instructions on computer organization architecture, where in this session we are going to discuss on one's complement representation. So we all know that one's complement representation is what? If you have a binary number with you, if you replace the values of zeros by ones and ones by zeros, we're able to achieve the representation in one's complement. Now, so the same number what we have used in the sign magnitude is what is being used here. The first bit is sign and remaining three bits are representing the magnitude. So 0, 1, 2, 3, 4, 5, 6, 7. In this way we represent it. And whereas here if we have MSB bit as 1, so that gives you before, if you look at the before representation here, in case of sign magnitude, whereas 0 to 7 values remain same. When it comes to minus 0, so it is this first bit is going to indicate the sign, remaining three magnitude indicates the number. Whereas in case of this minus 7, we are representing here, just take plus 7, wherever zeros are there replaced by ones, and wherever ones are there replaced by zeros, that will be one's complement representation. So which means, so 0 to 7 numbers we are going to write as it is, all right, and wherein we take the change here. So you see this one here, so plus 7 we have. If you want to get the ones complement of it, that is your minus 7, just replace the zeros by ones and ones by zeros. As we have 0 triple 1 here for this plus 7, so wherever 0 we have, replace 0 by 1 and 1 by 0, it gives you 1 triple 0. So this is minus 7. Similarly, check for 6, 0 double 1 0 becomes 1 double 0 1, right? Whereas plus 5 and minus 5 you can compare, 0 1 0 1 becomes 1 0 1 0, which means just replace the values of zeros by ones and ones with zeros. So that's how we can able to do it. And similarly, plus 4, 0 to 1 double 0, it becomes 1 0 double 1, which means you have 1 1 here, so it will become 1 0. In that way it will be functional. And where in 3 you check here double 0 double 1, it becomes double 1 double 0. And whereas plus 2, so double 0 1 0, it will be double 1 0 1. And plus 1, we have triple 0 1 and triple 1 0. And whereas zeros, all zeros are there, it become all ones. So this way the corresponding subtraction is implemented by using addition and ones complement technique. Still two representations are of zeros. So 0, if you see, there are two representations, which is all zeros and all ones. So this will cause some of the problems where we are able to do it not so easily. It leads to some confusions and some technical problems we may face during the executions while doing additions. Okay, this is about one's complement technique. And moving on to the two's complement representation, you just see here, two's complement representation is just adding. See this side, left side, what we are using from, sorry, right side, what we are using from 0 to 7, this complete arc is not going to be changed. So 0, 1, 2, 3, 4, 5, 6, 7. So the representation of that is going to be remain same. And wherein, if you check there, two's complement form, if you want to represent, it's one's complement plus 1. What we are trying to do here is we take the number, for example, and then we are trying to add that by plus 1, which means one's complement plus 1. So if you see this one here, it should be the representation of this one in one's complement form will be what? 1 triple 0. So for 1 triple 0, if you add one more binary number, it becomes 1001, which means, so in the previous case, this corresponding number will be having minus 7 means 1 triple 0. Now we are going to add plus 1 for it. It becomes 2's complement number. So that's why it becomes 1001. Similarly, you take up 6, 0 double 1 0 we have here. You do one's complement of it. It becomes 1 double 0 1, 1 double 0 1. You try to add 1 for it. So it becomes 1010. In that way, the numbers are represented. Okay. So this is how the functionalities of this is going on with two's complement representation. So we have seen three different types of representation. The first one is sign magnitude representation. The second one is ones complement representation. The third one is two's complement representation. There are three different ways of representing the numbers. And what is the advantage of using the two's complement representation here is we can able to understand that we can able to easily identify plus 0 and minus 0 in case of two's complement, because there is no question of minus 0. That's the problem what we encountered in one's complement. You see this one, for one's complement technique, there is plus 0 and minus 0, because 0 will be 1. It's plus or minus, it doesn't matter, right? We have two types of representation. So this is getting the confusion, or this creating the confusion. So to eliminate that, they have proposed a two's complement representation wherein there is no confusion with plus 0 and minus 0. That's the advantage of two's complement representation. And we can able to represent both the magnitudes of one's complement system, but two's complement system has only plus 0 representation. So that's the one of the thing. And we have for 4-bit numbers, the value minus 8 is uh, respectable only in two's complement system and not in other systems. So you can see this one here, only minus 8 we have seen in this two's complement system. We are not seeing that in anywhere one's complement or anywhere else. And it's more efficient for logical circuits implementation, and we can also afford to use in computers for addition and subtraction operations. So this way the two's complement technique will be helpful for us. If you look at this chart here, we can able to understand clearly the corresponding representation of that. So this is the binary value what we have completely here to here, whichever is zeros till here, till at this point, till here what we have, right? All of them are positive numbers. So plus 7, plus 7, plus 7. It is not going to change. Plus 6, plus 6, plus 6, plus 5, plus 0. The change is going to occur in this from here to here. Change is occurring from this position. Okay, from in this position, change is occurring. Where the plus 1 is indicating it's an magnitude of that as a minus. Okay, and then 0, 0, 0, it's 0, 1, 1, 1, it's minus 7. That's in case of sign magnitude. Once complement form, you're going to do the same number you represent in terms of minus 7, because how we got this, take plus 7, represent uh, zeros with ones and ones with zeros, it becomes minus 7. Say for example 0, 1, 1, 1. So replace zeros by ones and ones by zeros, it becomes ones complement. So that's how one's complement representation is done. And wherein two's complement representation, so this is already one's complement, we're going to add plus 1 for it, it becomes minus 8. Okay, 6 plus 1, it becomes 7, 5, 6, 4 becomes 5, 3 becomes 4, 2 becomes 3, 1 becomes 0. The point here is to eliminate this minus 0. How to eliminate this minus 0? If you can add a number for it, it becomes 1. So that's the point we are trying to understand here. So we have two zeros here in one's complement, plus 0 and minus 0. And two zeros have different numbers. We have 4 zeros here and 4 ones. To eliminate this problem, the proposal is being made for two's complement numbers. So wherein to minimize the confusion and use that in an effective manner. So that's how this one's complement and two's complement technique will going to work. Let us see one example of how to add the positive numbers. We have two positive numbers. If you want to add, so 0 plus 0, it's 0. 0 and 1, it's 1. 1 and 0, it's 1. 1 plus 1, it is 0. The carry is 1. So carry out is represented here. So that's how we're able to perform the addition of positive numbers. There's a pretty simple thing, what we all know it. So we'll see that in detail in further sessions. Thank you.